there, curious minds. Welcome to Physics Unlocked. I am Hajra Mughal and I am super excited to share this amazing topic with you. Today we are exploring a phenomena that's all around us yet often goes unnoticed. Say hello to Doppler's effect. The Doppler's effect was first described in 1842 by Austrian physicist Christian Doppler. But what is it exactly? Let me explain it in a simple way. So imagine you are standing in a pool of water. Now picture someone throwing stones into the water, creating ripples. As the ripple move towards you, they seem to bunch up, right? And as they move away from you, they seem to spread out. That's basically what the Doppler effect is. The change in frequency or wavelength of a wave, like sound, light, or water ripples, when its source is moving towards or away from you. Let's take another example. When a police car is approaching you with its siren blaring, the sound seems higher pitched. But as it drives away, the sound becomes lower pitched. That's the Doppler's effect in action. So the Doppler effect helps us understand how motion affects the way we perceive waves, and it has many practical applications in the fields like astronomy, radar technology, and many more. So let me recall again what is Doppler's effect in a simple words. When a sound source moves towards or away from an observer, or when the observer moves towards or away from the source, the observer experiences a change in the pitch. When it moves towards, he will be experiencing the higher pitch, and when it moves away, he will be experiencing a lower pitch. So in order to understand this phenomenon mathematically, we need to consider two key elements, the source and the observer. So in today's lecture, we will be exploring four different scenarios where one element is stationary and the other is moving, right? So let's start with the observer. Imagine being stationary and watching ripples move towards you. As the ripples approach you, they bunch up, creating compressions, right? Where the waves bunch up, we called it compressions. And as on the other side, it spreads out, and we call it rarefaction, right? If you can see in this figure, when the ripples are bunching up, it means they are creating compressions, and on the other side, they are creating rarefactions. So in simpler terms, when the waves move towards you, they compress, and when they move away, they spread out. So let's dive into the mathematical aspect of the Doppler's effect and explore the concept further. Okay, so let's consider the case where the source is moving towards a stationary observer. So we have two velocities to consider, the velocity of the source and the velocity of the sound, okay? The source, let's say a car, has its own velocity, and the sound it produces has its own velocity. So Vs is the symbol of velocity of the source, right? And V is the symbol of the velocity of the sound that created by the car, okay? So we know that the distance, one more thing, the distance between the two wave crusts, these are two wave crusts, right? The distance between the two wave crust is one wavelength, which is lambda. But if you can see in this video that when the source is moving towards the listener, the waves bunch up, right? You can see it is bunching up over here, right? Creating the compressions. And when and on the back side, they are spread out, creating the rarefaction. So this decrease the actual wavelength by the certain amount, which is the distance traveled by the source during one cycle, which we symbolized as lambda s. Basically, this is lambda. But when it is moving towards the observer, so they will, you can say, compressed out. So this lambda is decreased. Now, how much time it is decreased? It is, this lambda is decreased by some amount, which is called, we called it as lambda s. And what is that lambda s? It's a distance traveled by the source when it is moving towards the observer, right? That's why they are compressed out now. So we called it now this equation, after solving this lambda minus lambda s, so we called it as lambda prime. Lambda prime is the new wavelength, new distance we get after when the car is approaching towards the observer, and this is this compression. So this is the basically the first and the main equation. Okay, lambda prime, the apparent wavelength, is equivalent to the lambda, which is the actual wavelength between the two wave crust. And because this wave crust, the distance has been decreased because of the movement of the distance traveled by the source, it is symbolized by lambda s, right? Now just we need to substitute the formulas over here. So look at here, we know the formula of the relation between the velocity, frequency and the wavelength, that is v equals to f lambda. So if I wanted to find out the value of the lambda, so it will be v over f, right? So this is the equation, lambda prime. If I wanted to find the value of lambda prime, so what is lambda prime? Lambda prime is the new wavelength of the sound, right? So if I wanted to write this equation in terms of this, so it will be v over f prime. This is lambda prime, apparent wavelength, so f prime will be the apparent frequency, right? Second, lambda. What will be the lambda? Lambda is the actual wavelength. So the velocity of the sound divided by the actual frequency of the sound, जिसको we can give it symbol as fs, right? And the third is lambda s. Now what is lambda s? Lambda s is the wavelength of the the distance traveled by the source. S is the source, and it is equivalent to vs, velocity of the source, fs, the actual frequency of the sound, right? So when you substitute all this value, the equation will look like this. And you can see when fs is in the denominator, so we can take its LCM. So the equation will now look like this, v minus vs fs, and this left hand side is the same. Now if I wanted to find the relationship between the frequency, why I wanted to find the relationship between frequency? Because I wanted to see when the source is moving towards the observer, so he will be hearing a higher pitch. And the concept of the pitch is directly related to the frequency, right? So if I find out the equation of the frequency, so I can analyze the equation in terms of the pitch. Are you getting my point or not? Okay, so if I reciprocate this equation, so f prime over v, and it will be fs over v minus vs. Now take this v on the other side and fs on the separate. So f prime is the apparent frequency and fs is the actual frequency, and you can see from this equation that the numerator is greater because something is getting subtracted over here, right? So when the numerator is greater and the denominator is smaller, so the final answer will always be greater. So this equation represents that apparent frequency heard by the listener compared to the actual frequency emitted by the source. Since the source is moving towards the stationary listener, the listener perceives a higher pitch because this is the greater term, and resulting in the greater apparent frequency. So in summary, we can say that the source moved towards the listener, the apparent frequency is greater than the actual one. Apparent frequency is greater than the actual one, resulting in a higher pitch. Let's consider the opposite scenario when the source is moving away from the stationary listener. In the previous case, the source was moving towards the listener, resulting in compressions. As you can see in the figure, resulting in the compressions and the decreased wavelength. Now, as the source moves away, the waves are spread out. You can see from the back, the waves are spread out. So the increase in the wavelength is equivalent to the distance traveled by the source, lambda s. Now the wavelength has been increased. So the apparent wavelength is equivalent to the actual wavelength plus lambda s, because they spread out and the wavelength has been increased by how much amount? By the amount that is traveled by the source, right? So you just don't need to do anything, as substitute the value as we have done in the case 1a, and you will be getting the formula. If you compare this formula and 1a formula, the only difference is of this plus sign. In the previous equation there was a minus sign. So here we can say they see this. In this case, the denominator is greater and the numerator is lesser. As a result, the overall this factor is lesser, right? Indicating that the apparent frequency is lesser than the actual one. Apparent frequency is lesser than the actual one. This makes sense because when the source moves away from the observer perceives a lower pitch. The apparent frequency is lower due to the increased distance between the source and the observer. Okay, so in previous scenario, we have seen that when the source of sound moves towards you, the sound gets higher pitched, and when it moves away, the pitch gets lower. But what if you are the one moving? So if you run towards the speaker or the sound waves, you will hear a higher frequency because more wave crust will hit you per second, right? Conversely, running away means you will hear a lower frequency due to fewer wave crust striking you. Now this is the case too when the observer is moving towards the stationary source. As the source is stationary, right? So there is no velocity of the source. And here we have two velocities. One is the velocity of the sound because sound is traveling, right? And V naught is the velocity of the observer because in this case, now the observer is moving. So V naught is the velocity of the observer and there is no velocity of the source because source is stationary. But let's suppose if there is any speaker that is stationary, so it is emitting sound waves. So there will be the velocity of the sound. Okay. So now what's happening over here? Imagine a wave crust. If you can see in the diagram, the wave crust just reached you. The time it takes for the next crust to hit you is the period you will observe. But if you were standing still, you will simply wait for the next crust to arrive, right? If you were standing over here, you will wait for the next crust to arrive, which would be the actual period of the wave emitted by the speaker. But if you are running towards the speaker, you will meet the next wave halfway, right? Because the wave is also moving towards you and you are also going towards the wave like this. Now, so you can say if you can figure out how long it takes for the next crust to hit you, so that will be the time you will experience. So what is happening? Because this person is moving towards it, so the the distance has been reduced. So basically what is happening, the new wavelength which we have experiencing, that will be lambda minus lambda naught, because lambda is the actual wavelength and it is decreased by the distance that is traveled by this observer. So when it hits the next crust, wave crust, that is because it is hitting it more frequently because it is moving towards the source. So this is the equation, which is the main equation, and when you substitute the formulas in it, and you will be getting the final equation like we have done in the previous derivation. So we know that the formula is basically V equals to F lambda, and we know that if I replace frequency with the time, so it will be 1 over t because frequency and time period are inversely proportional. And if you can take this t on other side, so lambda basically will be V into t. So why we are doing this? Because we are talking about the period, the decrement in the time period because of the frequent waves. More waves are frequently touching the observer, passing the observer. So it's up to you, totally up to you, that you will be doing this derivation in terms of frequency or time period. I will substitute the value in terms of the time period. Then in the end, I'll change time period with the frequency. Okay, so just substitute the value. So lambda prime, if you see this equation, lambda is equivalent to V into T. So lambda prime will be V into T prime. What is V? Velocity of the sound. T prime is the time period that is the observer experiencing because of the movement towards the source. Lambda is the real or the actual wavelength. So this is the velocity of the sound, the real time period, the actual time period, minus lambda naught is the distance traveled by the observer. So the velocity of the observer and the time period observed by the observer, which is the apparent one, right? So if I take this v naught t prime on this side, so it will be written with the plus sign, right? And what is the common term over here? The common term is t prime. So if I take t prime common, so it will be v plus v naught. And if I take that v on the other side, okay, so this is how the equation look like, this term on this side, right? And if I replace t with the frequency, first I will reciprocate it, and if I replace 1 over t with the frequency, this is now equation. Now what is f prime? F prime is the apparent frequency, f is the actual frequency, and simply if I wanted to know what is this bracketed term, so you can see the numerator is greater and the denominator is lesser. So this term will be greater one. So you can say that the apparent frequency is greater than the actual frequency. It means that when the observer is moving towards the stationary source, he will be having a higher pitch, right? Now in this case, when the observer moves away from the stationary source, something interesting happens, as you can see in this video. When the listener moves away from the source, now it moves away from the source, they encounter wave crust less frequently. This means the distance between wave crust appears to increase, effectively stretching the wavelength. The observer is moving away from the waves, increasing the apparent wavelength. What does it mean? If I wanted to write the equation, so the actual wavelength remains same, but the distance traveled by the observer adds up to the wavelength, increasing it. So this is the results in longer apparent wavelength. So if you compare this derivation with the previous one, there was a minus sign over there because when it was moving towards the source, so the distance, the wavelength got shortening. But now because it is moving away from the source, so the less wave crust encounters with the person, with the observer, so the wavelength has been increased by how much amount? By the amount traveled by the observer, right? So same, if we substitute the values as we have done in the previous derivation, we will be getting the same formula with only the difference of this minus sign. In the previous derivation, there was a plus sign. So if I analyze this equation, so the numerator is lesser now and the denominator is greater. So the overall bracketed term will be the lesser one, right? So what we can say, this equation shows that the observed frequency, or you can call the apparent frequency, is lesser than the source frequency. And you can say that when the observer is moving away from the stationary source, obviously he will be getting the lower pitch. So that's all for today. Thank you for tuning in to the Physics Unlocked. If you enjoyed this video, please consider subscribing to my channel for more engaging physics content. Your support means a lot.